Hi class, in 13.6 we will be looking at the area of regular polygons. The learning targets for today, we will be calculating the area of regular polygons, writing a formula for the area of a regular polygon, and then, as we have been doing with the other lessons in Chapter 13, calculating the area of composite figures. If we take a look at the lesson introduction for today, it says, have you ever noticed that every stop sign looks exactly the same, every yield sign looks exactly the same, and so on? This is because the Federal Highway Administration has standards that indicate the exact sizes and colors of roadway signs. Most of the sign shapes are polygons. At the start of problem 1 on page 884, let's take a look at 3 street signs and answer the question, how big is that sign? What I would like you to do with your group members is number 1, number 2, and then number 3 at the top of the next page. I want you to look at the yield sign, the do not enter sign, and the stop sign, and look at the specifications and answer the questions that go along with it. Go ahead and do that with your group members. If you take a look at the yield sign for number 1, what is special about that triangle that forms the yield sign? Hopefully you can see that the sides of the triangle are all the same length and the angles of the triangle are all the same measure. We would call that triangle equilateral and also equiangular. For the do not enter sign in number 2, what is special about that quadrilateral? The sides are all the same length and the angles all have the same measure. This quadrilateral would be classified as a square. If you look at number 3, the stop sign, what is special about that octagon? Again, all of the sides are the same length and the angles have the same measures. Continuing on page 885, the polygons in questions 1 through 3 are special polygons called regular polygons. 2 other possible sizes for a yield sign are shown. Take a look at number 4. Would these signs be considered regular polygons? What can you conclude about all regular triangles? Yes, these 2 triangles would be regular polygons because the lengths of the sides are the same and the angle measures are the same inside of the triangle. And you can hopefully see that each angle inside any regular triangle is going to have a measure of 60 degrees. Number 5 asks you to calculate the approximate area of the yield sign from question 1. The approximate height is drawn in for you. And in number 6, it asks you to calculate the approximate area of the do not enter sign from question 2. So go ahead and do number 5 and number 6. Use your prior knowledge of the formulas for a triangle and for a square in order to find the area. If you take a look at number 5, the area of the yield sign would be approximately 390 square inches. Remember, the formula for the area of a triangle is 1/2 base times height. For number 6, the formula to find the area of a square is s times s, or s squared. Each of the side lengths are 30 inches. 30 times 30 gives you 900 square inches for the approximate area of the do not enter sign. Let's turn to page 886. If you take a look up at the top, it says when 2 polygons are exactly the same size and exactly the same shape, the polygons are said to be congruent polygons. Number 7, to calculate the area of the stop sign from question 3, you can use the fact that a regular polygon can be divided into triangles that are all exactly the same size and same shape. The bases of the triangles are the sides of the polygon as shown. In this case, the height of each triangle is approximately 15 inches. Calculate the area of the stop sign, round your answer to the nearest tenth if necessary, and explain your reasoning. So go ahead and do number 7 with your group members. So the first thing you would have to do for number 7 is figure out the area of one triangle. If you follow the formula for the area of a triangle, A equals 1/2 base times height, you're going to end up with 93 square inches. Since there are 8 triangles that would be inside of that octagon, you're going to multiply 93 by 8 for a total of 744 square inches. Take a look at the bottom of page 886. It says the height of the triangle in the stop sign in question 7 is the apothem of the octagon. The apothem of a regular polygon is the perpendicular distance from the center of the regular polygon to a side of the regular polygon. Number 8 asks you to draw a segment that represents an apothem on each regular polygon shown. The center of the polygon is marked by a point. I just drew in an example of what it could look like for both of the polygons shown, the hexagon on the left and the pentagon on the right. Take a look at page 887, and what I would like you to do is number 9 and number 10 with your group members. In number 9, you're going to calculate the area of the hexagon and explain your reasoning. And in number 10, you're going to calculate the area of the heptagon and explain your reasoning. Please make sure that you are showing your work. Go ahead. For number 9, you are going to find the area of one triangle. You are going to get 692 square centimeters. You're going to multiply that by 6 then, because there are 6 sides in a hexagon. Your total area then for the hexagon is going to be 4,152 square centimeters. For number 10, same process. The area of one triangle in the heptagon is going to be 33.2 square meters. If you multiply that by 7, you're going to get 232.4 square meters for the total area of the heptagon. Take a look at the top of page 888, and to finish off problem number 1, now we want to try to come up with a formula in which we can find the area of a regular polygon. So go ahead and answer number 11 and number 12 with your group members. Refer back to the questions that you just answered, the steps that you walked through in order to figure out what the area of these regular polygons were, and see if you can come up with a formula. For number 11, if you've referred back to the answers that you came up with on the previous pages, you can calculate the product of 1/2. You can look at the number of sides in the regular polygon, the length of one of the sides, and the length of the apothem. All of those are going to factor in as far as figuring out the area of the regular polygon. Number 12 says now to write out a formula for the area of a regular polygon with n sides. It says to use A for the length of the apothem and L for the length of one side of the polygon. So here is what your formula should look like. The area is going to be equal to the quantity of 1/2 L times A times N. We are going to skip problem 2 in 13.6, so let's move ahead to problem number 3 on page 890. What I want you to do is calculate the area for number 1 and then number 2, A and B. You can skip letter C. So go ahead and take some time. I wrote the formula in order to find the area of a regular polygon on the screen so that you can refer to it. Make sure that you add this to your word map as well. This should be the final formula that you need to complete that. Go ahead and take some time to do number 1 and then number 2, A and B. This formula should be fairly easy to follow. All you have to do is really plug the values in as you're going along. For number 1, we have 1/2 times 24, which is the length of one side, times 33, which is the length of the apothem, times 9, which is the number of sides for a nonagon. So we would end up getting 3,564 square feet for the area. For number 2, we would have 1/2 times 20, which is the side length, 24.1, which is the apothem, and 8 is the number of sides for an octagon, 1,928 square inches. For letter B then, for number 2, again, following the same formula, plugging those values in for each variable, 475.2 square inches for the area of the smallest possible stop sign. We are also going to skip problem 4 in 13.6, so you can turn to page 892, and your homework is going to be problem 5. Again, you have a composite figure. Write down some strategies that you can use to find the area of the shaded region. And in number 2, you have to calculate what the area of the shaded region is going to be. Take a look at the word bubble. It says think back to all the composite figures that you have worked with in this chapter. Hopefully you can see that you used similar strategies to figure out what the area of the shaded region was going to be in each. So go ahead and do that for homework. Let me know if you have any questions regarding the area of regular polygons. Thanks.